So welcome back, everybody. What we are going to do today is actually to look at some of the things we started with last time. And this is about diagram rules. And we are going to look at the terms in perturbation theory and how we can actually calculate them and how we can represent these in terms of diagrams. The diagrammatic representation is extremely powerful in both quantum field theory and many-body physics. We have mainly dealt with time-independent many-body physics, but if you bring in time, you're actually doing essentially the same thing as you would do in quantum field theory, except that in our case, we are dealing with non-relativistic quantum mechanical problems. But much of the same rules which you see, either we're dealing with time-independent or time-dependent perturbation theory, or Green's function theories, copper cluster theory, which is another popular many-body methods. It's pretty common to express everything in terms of diagrams. And that gives us a very compact formalism by which we can identify contributions to the either perturbative expansion, or if we are dealing with copper cluster theory, expansion in copper cluster theory to a given order. Then we are going to look at more examples, and we are going to set up the diagram rules, which actually are a diagrammatical representation of applications of Wick's theorem, nothing but that. And that gives us some specific rules so that we can look at a diagram, and then from that we can derive immediately the analytical expression for the diagram. And then when you have the analytical expression, then it's up to you to actually go and set up a code or write down the different contributions which appear and calculate the final expression. So this is roughly the kind of strategy which we will deal with today and also tomorrow. I also want to say that tomorrow, since I will be busy with a workshop, for tomorrow there will be a recorded lecture. So we will not meet here. And the exercises are these exercises for week 45. And they contain essentially a kind of repeat with application to that simple two-level system which we looked at previously. And then you can find the material here on many of these things in chapters 5 and 7 in Sherwitt and Bartlett, but also the whiteboard notes. And in the slides here, we would also have some material on the derivation of the diagram rules. And I also wanted to repeat one of the messages which I sent by email to all of you, and that's about the second midterm, because many of you are also busy with a project in another course, and that has a deadline this coming Monday. So I thought that we could start with a midterm next Friday, and then we have a deadline till November the 24th, if that is okay. As far as I could see, that seemed to fit everybody. So I hope it doesn't interfere too much with other activities. Yeah?
We have much more time on this one.
No, it's the same. It's 10 days. Yeah. No, that's fine. That's fine. So I normally just said 10 days. I mean, we have the Friday next week, and then we will spend some time on discussing the midterm during the exercise session. And then we have the whole week thereafter, and then the deadline on the Monday. Okay. Goodie. So what I'm going to do now is basically to switch back to the whiteboard, and we are going to look at the things where we stopped last time, and bring up some of the arguments which we put up there. So last time what we did was to set up a way to represent in terms of mathematics, but also diagrams which appear to second order in perturbation theory. So let's repeat some of these things, and then we are going to look at the other examples and how we can represent these things diagrammatically. So when we've gone through the equations, then we will try to express this in terms of specific rules, so that if I give you a diagram, you can look at that diagram, and from these rules, you can extract the analytical expression. Now, diagrams, the way they are drawn, also reflect specific symmetries in the interaction. And people have actually used this kind of graph theory to generate high-order contributions in perturbation theory. That's a pretty common recipe, which many people have been using. But let's now look at the things which we did last time. So last time we looked at many-body perturbation theory to second order. And we labeled this as a delta E0 with a 2 here, a superscript 2. And that was given by an expression where we had a sum over intermediate states. We had the ground state. So we are still assuming that there is one and only ground state. We are assuming that it's a non-degenerate. Then we had the interacting part of the Hamiltonian, which contains both a one-body piece, which was our Hartree-Fock potential. And then we had the intermediate state, lambda, and these are obviously different from phi 0. And then we had the h of I and phi 0. So this is the general expression which we got to second order in Rayleigh-Schrödinger perturbation theory. And this epsilon 0 is the non-interacting energy of all single particle states for the ground state, minus the sum of all the non-interacting energies for the excited state. Now, what we did then, when we broke this down, is that we found two specific contributions. One, which we label as a one-particle, one-hole diagram. That was one of the contributions. So that means that the intermediate state, which you had here, was a one-particle, one-hole excitation. And we calculated that one. And what we found then is that this expression became equal when we break this down in terms of Slater determinants and the single particle states. Then we had the AI, which then correspond to the intermediate state. And then we have this summation over J and K. So the I, J, and Ks are below the Fermi level, and the A's are above the Fermi level. And what we ended up with then was a sum, or we have these specific states, G, we have an interaction piece, we have an A and J, and then we have an anti-symmetrized matrix element, we have an A and K, again, the interaction piece, and then we have an I and K, and this is also anti-symmetrized, and this was divided by the particle energies minus the single hole energy and the single particle energy. That was a term which we label as a one particle, one hole piece. Then we found the next expression, and the way we did this was simply to calculate these different terms, as we did before, actually these terms. And we did this when we derived the Hartree-Fock equations and also the different terms to configuration interaction theory. So what we found then was that this term was then given by a factor of 1 divided by 4. There is a sum over two particle states. So this represents a two particle, two hole excitation. And then we had an IJ. And here we just simply use the standard contraction rules. Still anti-symmetrized. So there are two contributions. We have an AB. And then we have the IJ. So the AB represent the intermediate states, which have then been promoted from below the Fermi level. We pick two whole states, I and J, and promote them to particle states. And that gives us a contribution where we now can calculate term by term the contribution to the configuration interaction wave operator. So the terms which you see here are terms which we now can also find similar contributions to if we go to third order, fourth order, etc. But the diagrammatical approach is much, much more compact. And then a diagram would then simply represent all these expressions, which we are going to look at now. So let's remind ourselves a little bit about how we set up things. And let's now look at this from a more general term, more general point of view. So the way we can think of this specific contribution, which you see here, is as follows. So we can now start up here with the ground state. This is a state we are ending in. And this is a state which we, in second quantization, would then represent by a product of creation operators. And we can express this as lines here up to the final one. So this would be H1, H2. These are the whole states, the states below the Fermi level, up to the last state below the Fermi level. Now, if we then look at the expression which was, so this is our end point. Now our starting point is a phi 0 here, which we also would write out in a much similar way. So we would have the H1s, H2s, etc. So we can indicate these by the different arrows, H2, H3, up to Hn. So that's the state. If we write it out like a product of a sum over I equals 1 up to n, and then we have the Hi acting on the true vacuum state. Now, in between here, if we now look back at the expression which we had, if you look at the expression here, what we have is now an interaction which takes place, and the state gets excited to a two-particle, two-hole state. So the way we can draw this now in a very generic way is that in between here now, we have an interaction. And this interaction could be, and I'm not putting label on it because we're not performing the contractions yet. And then we had the two-body interaction, but we had also the Hartree-Fock potential. So this is what we called V. And then we had the the one-body Hartree-Fock term, which is something which we called for a U Hartree-Fock. So this is a one-body operator, and the other one is a two-body operator. Then in between here, what we have is now an intermediate state. So we have this phi lambda, so this is we just write this H of I is now represented by these two possible contributions. So essentially what we did last time was to actually use Wick's theorem to calculate the contribution to the energy, which are those two contributions we have on the previous page. Then in between here, what we have now is a intermediate state. And then we have an epsilon 0 minus this epsilon lambda. And we could write the intermediate state if we now are dealing with everything in the particle formalism. So now we are actually looking at this in terms of all the lovely 9 n particles which are interacting in the system. So we are not introducing yet a particle hole formalism. And you see that this becomes quickly unwieldy because we have so many particles. If we have 100 particles below the Fermi level, then clearly you would have to draw all the different possible contractions which can take place. Now, somewhere in between here, something happens. And what we did last time was to draw this particle state like this. So we would have a PA and a PB. That's a two-body state or two-particle state. But we could have a one-particle excitation as well. And this continues all the way to the final one. And then in here again, we have the interaction. And these states have to be contracted with one of these two pieces. So this is how you could, in a diagrammatical, or we might better say pictorial way, express this physical process. And then you can really, if you look at this contribution, which you have here, for instance, you could now think of this being a ground state. The interaction acts on it. It perturbs the system, and it creates a two-particle, two-hole excitation. Then the system interacts again, and it brings everything back to the ground state. So it de-excites a two-particle, two-hole excitation. So if you look at all these possible contractions, we can then, if we now look at what we have here, you could now think of, let's say, H1 being contracted here, H2 with that one. And then these two guys could contract here and there. And then again, they could link up with this one, like that, these legs. And finally, we could have this coming up here. So the way we would write this then would be something as follows. So if you take this example, because you have so many possibilities, but this translates into the following. So it translates into a summation over Hi, Hj, and then I have a Pi, Pj. And then if I leave this in the particle formalism, so I'm not setting up a whole particle hole formalism. So I would have an H1 here. So these are just bystanding particles. And then I have an Hi minus 1. And they have been contracted with each other. But then in between here, we now draw this as a more compact diagram in the particle formalism. So we would now have an intermediate state here with a Pj and then a Pi, and then I have an Hi here and an Hj. And finally, this goes out in an Hi, Hj, but it doesn't need to be the same states which are in the beginning and in the end here. And then finally, we have a set of final contractions which are not affected by the interaction here. And then H of n. Now we have to be a little bit careful because I said these two guys here could in principle link other states. But if we do that, then there will be some Kronecker deltas with states here which are not linked to its corresponding state. So due to the fact that only two particles interact at a time, it means that the other n-2 particles, they have to find their own partner or peer. And due to the orthogonality of the single particle basis reflected in the anti-commutation rules, this gives a Kronecker delta. And that means that the only possibilities you have would then just be this sum. Now, normally what happens then is that we leave out all these Kronecker deltas, and this diagram would then be written out as an H of I, H of J, and now we are writing this in a diagrammatic way, and I would have a term which goes like this. So this is one possible contribution, and then I have the dotted line here. This is the particle state, and then I have my Hi, Hj, and then Hj of Hi, and then I have my P of, I should actually write Pa and Pb here. Pa and Pb. This is the way we would write it. And then in order to get rid of the summation sign here, what we would typically do then is simply to bring back the two whole lines and just join them. So the whole lines will be lines which go downwards in the diagram, in the expression. So this is something which we then would write like this. So we would have an H of I, and then we have a P of A, and then we have an H, a P of B, and finally an H of J. And often what we do then is simply to skip this notation with H of I and H of J. If we now reserve the letters I and J, K and L and so on to whole states, we would simply write this one as an I and J and then A and B. So this would be the way by which we would think of this physical process. And if you now look at what we have here, what we do here is that we create a two-particle two-hole state. And then we create a new two-particle two-hole state here, which then de-excites the system. So we excite the system from the ground state to a two-particle two-hole state. There is a new interaction, which then brings us back again to the ground state. So this is the way you can assign a physical way of interpreting this diagram. Now, in principle, the system interacts, the particles are interacting with themselves an infinite amount of time within the Heisenberg uncertainty relation condition. So in a certain sense, every term in perturbation theory is just a term in a long, long sequence of such contributions. And if you go to third order, there will be new two-particle two-hole excitations, which actually will then correspond to four-particle four-hole excitations, etc., etc. So you see now that the way we can express something like this term here, which represents a two-particle two-hole excitation and then de-excitation, you can think of this as a set of physical processes. It's actually not fully correct. So some people think that the diagram represents a physical process. If you go to field theory, people actually think that specific Feynman diagrams represent a physical process, but it's actually the infinity of such processes which represent a specific physical process. So that's something to keep in mind. But it's a very useful way of labeling specific contributions in perturbation theory. So you would then typically say that this represents a two-particle hole diagram. Now, this guy here, which we have, that comes from these states here, now where one of these is contracted with the one body potential. And then clearly, since you then only have one free, that will have to contract with only one of these. And then this has to then be matched with that one, because then you would create a one particle, one hole state. If you try to connect that with a two particle, two hole excitation from the two body force, that will give you a contribution which is 0. So the only possibility is that this one picks one guy here, this guy picks the one body potential, and then it gets de-excited. So that will be a one particle, one hole excitation. The way that one is going to look like is something like this, when I now write it down in a similar way. So what I would get then would be something which looks like this. So I would have a summation over hole states, HI, HJ, and HK, and then I have this particle state P of A. So I would have an interaction piece here. So now I'm writing this in the particle formalism. So this would could look something like this. So this could be one of the many contributions which we have. And then we would now have a hole state which comes in, and this is the hole state HJ, becomes a particle state P of A here. And then I have a new interaction. This hole state HJ leaves here. And then I would have a hole state H of K and H of K here. And then we put arrows because everything is in the particle formalism. But this is something, when I now look at it, this is something which I can draw like this. So I can close the whole loops. So I'm just bending these lines here and force them to point downwards. And I join them because you have the same state there. And instead of writing the summation, we simply now mark that as a closed loop. So that's the mathematical origin of these so-called closed loops. And then we have the interaction. We have now the particle guy, which comes up here, which we are now simply going to label as an A and A. But then we have the whole state here, which is our state J. And then finally, we have a term like that, which is our state K here. We could have labeled that one because the interaction is symmetric under the exchange of two particles. That means that this guy here could actually be written like this. It will give rise to exactly the same mathematical expression. So we would have a K here, we would have an I here, and then we would have a J and an A again. Now, when we look back at the expressions which we derived last week, then this translates into the following analytical expression, where we have a sum of I, J, and K. These are the states below the Fermi level. Then I pick the interaction elements. So in that specific case, I will have an interaction with a left state K. So it means that I need to have a K. I normally start with when I write the diagrams, the expressions for them, I typically start with the first interaction vertex, and then I just go down in the system. So what you would have then would be a state K, which is to the left. And then I would have a state J, which is actually leaving here. So if I bend it up again, it's actually a J which leaves. So that means that I should put a J here. And then I have my V. And then I have my K, which is also entering. But then I have an A, which is entering to the right of that vertex. Then if I take the next one, what I have is a state I. And I have a state A leaving. I have my interaction element, and then I have a state I coming in and a state J leaving, like that. Wait a minute, no, so that should be K. No, sorry. This is actually J, and that is K. No, sorry, that is I. That's an A. Yeah, there's a J there, exactly. Okay, and then I have an energy denominator. And the way to think of the energy denominator now, because we're going to set up the kind of rules for calculating these terms, if you now draw a line in between here, because that energy denominator is going to be the difference in energies between the excited state. So if you look back here, there's going to be an excited state, which is a one particle, one hole excitation. And then you have the sum over the single particle energies from the ground state. So when you do that intermediate state there, what you're going to get now is simply an epsilon j minus an epsilon a. So what we did here was simply to count the number of intermediate particle states and hole states and set up their energy difference. So this is the expression which we ended up with last week. Now, if I flip this vertex into that expression, or that diagram, the only thing which will change then is actually the order between K and J and K and A. So if I flip it over to that one, what will happen then is that I will have AK and JK. And when we use these anti-symmetrized matrix elements, this is exactly the same mathematical contribution. So what we would say then is that these two diagrams, these two here, are normally what we call topological equivalent. It's because the only thing we do now is just to twist lines or twist the positions of the states. So we would get exactly the same equation, topological equivalent diagram. So let's look at what this actually may mean. So I guess it's not that difficult to convince you that if I just flip this one over like I did here, the only thing which happens then is that I just interchange J and K and A. And due to the way we have defined these integrals or these elements, then they represent exactly the same expression. So mathematically, when we write down the expression, we get the same contribution. There are actually, of this type of diagrams, there are 16 topologically equivalent contributions. And the reason for why we don't have a factor of 1 over 16, because there's a factor of 1 over 4 from each one of these, is simply because we have 16 equivalent contributions which sum up and then cancel the factor of 1 over 16. Now, yeah. So mathematically, it means that the expression for the contribution to the energy is exactly the same.
So,
and they are equivalent because the interaction has specific symmetries. And the symmetry which you have with this interaction here, if you look at it, so if you write down this one, it would be a state J and a state K of V, and then I have my state I and K. This is the same when it's anti-symmetrized, but also when it's not anti-symmetrized due to the interchange of two particles, this specific symmetry, this is exactly equal to the same term here of Ki, A, anti-symmetrized. Which again, I could now actually take an exchange term, which would be the same as J of K or V of Ka, anti-symmetrized, etc. So when we draw these diagrams and say they are equivalent, it simply means that they yield the same mathematical expression at the end. And in total, when you perform the contractions, there will be 16 different types of contributions, and they then cancel that factor of 1 over 16, which we would get due to the interactions. So you can, if we now move on a little bit, we can look at another contribution to this second order type of diagrams. And let's look at a term which looks like this. So we take now this term and just draw it. So this is just one way we could open up the contributions from this second order term. And then we have a state J here. We have the state A here. And then we have the state, so let's just write this, that was an I, and this is a K here. So if I want to set up the interaction elements, so the first thing I would do then is simply to set up the interaction elements. So I would have a K on top here, so K going out, and then there is a J going out to the right. There is a interaction piece, and then there is a K coming in, and then there is an A coming in, anti-symmetrized. And then I have on the next one, I would then have a J, or actually an I coming in. Sorry, leaving. And then I have an A leaving, and V, and then I have an J coming in, and I have an I coming in, and this is anti-symmetrized. Now, if you look at this term, which you have here, this specific term is actually equal to, if I now keep this first term as it is, of Vj of Ka, anti-symmetrized, but then I would have a minus sign, which now comes from the interchange between I and A, and V and I and J, anti-symmetrized. So this is me just setting up the contribution from the two interaction terms, these two. So let's just write this down here. So if I take that one, I have this, and if I take this one, that gives me this contribution. Now, I haven't set up any summations, no, nothing. Now, if you look at what we have here, this one, if I go back to what we set up previously, if you look at this diagram here, this one, the mathematical expression you have, which is this, is for the two interaction pieces, is the same as this one, except for a minus sign and the interchange of I and J here, J and I, which we have here. So it means that if I look at this term, this is the same as what I have here, except that there is a minus sign. That's the main difference. So when I'm looking at this contribution to second order, I could pick this one. That doesn't have a minus sign. If, on the other hand, if I started with this one, and I want to relate it to the previous one, there is a minus sign I need to take into account. If I also look at what we have here, we have now a summation, which we have performed over the intermediate states. So here there should be a sum over I, J, K, and A. And then if I look at the states in between, if I look at the energy, possible energy denominator contribution, this is the same as before, epsilon J minus epsilon A. So this term, which you see here, is equivalent to this term here, except for a minus sign. So we would also say that that is an equivalent diagram, because I can always, if I now decide to have a specific ordering, so that these states are ordered so that I comes before J, then I could actually opt for only this representation for all the different 16 possibilities I would have to second order. So with anti-symmetrized matrix elements, I could simply now say that this term here, where I have skipped now AS, but you should also put in AS back again, I could simply use either this term, I could use that term, or I could use this term here. So when I perform the contractions, I get the specific elements for the integrals, and I can rephrase them in terms of a diagram. So what you see now is that what we are doing is that we are taking the vertices and converting them back into the integrals, which we could typically have in a table. We need to put in an energy denominator, which is the energy difference between the state here and the state here. And we do that by simply counting the difference in energy between holes and particle states. And that is what this is. Then the minus sign here arises from the way we have ordered the contractions. And there is a rule which we're going to set up now before we prove it. And that rule is simply going to say that there is a phase factor, which is given by the number of hole states plus the number of closed loops. So this diagram here has now 1, 2, 3 hole states. It has one closed loop, but this is also counted as a closed loop. And In that case, we have 2 loops and 3 whole lines. So that means -1 to the power of 5, which gives -1. If I go back to this diagram, I have 1 loop here. This is a closed loop. This is a loop. This is a loop also. Ends at the same interaction, starts at the same interaction, ends at the same interaction. And in this case, we have 3 whole lines. So that gives us -1 to the power of 6. And that comes with a factor of plus. So these kind of rules are nothing but plain reflections of the way we perform the contractions using Wick's theorem. And that's something we will prove a little bit later here. And you will find that material in the PDF file of the slides for this week. And the reason why, as I wrote in an email, well, you will only find the PDF is that MathJax does not allow you to use contractions, Feynman rules, etc. It's much more difficult to bake that in a Jupyter notebook. So for some of the lectures which are coming, you will basically just get a PDF file for the weekly material, simply due to that. That's the main reason. If somebody cooks up a way to represent the contraction by Wick's theorem with MathJax, I would very much like to see that. Okay, so if we now look at the other example which we had, if we look at this diagram here, which now represented this second order contribution with a 2-particle, 2-hole intermediate state, there is nothing which hinders us in changing a little bit the order of the particles and the whole states. So I could actually rewrite this in the following way. And now let's try to convince ourselves that this expression here is going to give us the same expression as we had previously. So one thing which we could have now, if I just keep the particles like this, so A and B end at the same vertex and start at the same vertex as in the previous case, but then we could have an exchange term coming from the whole states, I and J, and this is A and B. So let's now look at the diagram, the expression which we set up. If we now just go and look at the vertices here for the interaction, for the top here, we would have I and J, and then we have V, and then we have A and B, and now I'm skipping this anti-symmetrization sign or symbol because I'm assuming now that all the integrals which we're looking at contain a direct term and an exchange term. So if I only look at the vertices, I'm not setting up the final expression, I'm just looking at the vertices because those are the quantities which allow us to say whether the contributions are equivalent or not. If I look at the next one, this is going to contain now I and J as before. I have a V, A, B as before. I have A, B, V, and JI. But we know now that this is the same as minus of the previous case. So we would say that that contribution is equivalent to the previous one, except for the minus sign. This minus sign comes by because we are crossing the whole lines, and that means that there is a set of operators here where we have an AI leaving, and then there's an AJ, and we're performing the contractions, and then we have to swap operators in order to bring them together. And that means that we get a contribution here now, which has a minus sign. If we draw it like this, then this is equivalent to this expression here, except for a minus sign. So when we are then performing the calculations, then due to the different contractions which we're performing, when we do the contraction, there will be a minus sign here, and that minus sign will then take care of that minus sign. So at the end, when we set up the final expression, there's going to be a plus sign. So if I now look at this expression here, when I now set up, and I haven't given you the rules, if I take this term here, now there should be a factor of 1/4, That is another rule which I'm going to set up pretty soon. A, B, I, J. And then we set that as a minus sign. And this is an IJ of V of AB, AB of V of IJ. So that is exactly the same as we had before. And then I set up an energy denominator here. And that is going to give us the difference between the whole states and the particle states, the single particle energies, minus epsilon A minus epsilon B. Now, this specific case here is actually not equal to the expression which I get if I take this one, because that one will have 1 divided by 4. And then it's going to be an A, B, I, J. And it's going to contain exactly the same integrals of A, B, V, and I, J. And then I have an epsilon I plus epsilon J minus epsilon A minus epsilon B. However, when we did the calculations last time, we found that this minus sign here needed an additional minus sign. And that came from the fact that we had to swap operators here. So when we did that, this also came out with a plus sign. That means that we need to be a little bit careful with the way we define the final rules for the diagrams. So let's try to set them up. Because now, in order to get rid of this one, there has to be a minus sign which comes from a specific factor which we assign to the diagram. And one of these factors is actually a factor which is simply follows from Wick's theorem and the way we have to swap contraction or operators in contractions. And this is going to be given by the number of holes plus the number of loops. So in this case, we would count the whole diagram as a closed loop. So that's a +1 loop. And we have 2 whole lines, this one and that one. So that gives me -1 to the power of 3. -1 times -1 gives us a final plus. This dude which we have here has 2 whole lines and 2 closed loops. So that gives us -1 to the power of 4, which is plus. So this is what we did here in order to get the right expression, which we derived last week. We need a rule now which, if I was to open up the diagram and write it like this, then from the rule, you would have to extract the correct mathematical expression. So the correct mathematical expression, which we derived by doing all the contractions last week, is this one. And when I now set up a diagram, I can draw it in different ways. So there are equivalent ways of setting up the diagrams, which gives us exactly the same expression. So this is what we want at the end. And what you would typically do is just to draw one diagram. And when you open it up, it should give you an expression which comes from many different types of contractions. So let's set up the rules without proving them, okay? So the diagram rules. And you will find the same in the lecture notes, plus some kind of semi or pseudo mathematical proofs for the different base rules. So the diagram rules, I mean, the first rule which we have is actually pretty simple. And that is that we have to draw all equivalent diagram, draw all distinct diagrams. They are normally called topologically distinct diagrams to a given order. So if you can rewrite a given diagram in terms of something which gives exactly the same contribution, that would not be a distinct diagram. That would be the same type of diagram. Draw all distinct diagrams to a given order. By linking, so let's just write this one, by linking a particle and whole lines with different interaction vertices under specific restrictions. By linking up particle and whole lines, particle and whole lines lines with different interaction vertices. Different interaction vertices under the following restrictions. Under the restrictions that and then A, and then there is a B, and there is a C. But before we say A, we take a break, which I think you all deserve here. So let's take a small break before we set up the restrictions by what we are going to use as a definition of a distinct diagram. So let's do that and take a small break. Okay, so before the break, we started to set up the diagram rules. We use some diagrams as an example, but without setting up the rules. So what we're going to do now is to do this in different steps. So first I threw you out into deep waters. Now we're going to set up the rules so you have some guidance to get out of deep waters. And then after that, we are going to actually derive the rules. But the rules follow simply from applications of Wick's theorem. It's nothing but that, some of these rules actually. So when we are setting them up, this becomes a very powerful recipe for writing down contributions to given orders in perturbation theory, but also to identify which terms contribute and which do not. So when we are moving into copper cluster theory, we can derive the equations algebraically. That is the way I actually did in the beginning. But you can also derive exactly the same equations using diagrams. And then from the different possible contractions, you can actually see from the diagrams that these are the terms which should be there. And that's it's a very powerful way. And at the same time, it's also a way to think in terms of physics. And as I said, these diagrams, which we had to second order, one represents a physical excitation, like a one particle, one hole, and the other one is a two particle, two hole excitation. And when we then look at contributions to the energy, we can try to figure out which one is most important. Sometimes it could be one particle, one hole excitations, which play a big role, and other times a two particle, two hole. So if you go back to the Lipkin model, which we had back in the first midterm, in that case, we had an interaction which consisted of one operator which created a two particle, two hole excitation, and another operator which created a one particle, one hole excitation. And in many cases, these are often the driving excitations in a physical system. So a one particle, one hole excitation can often be linked to, if you're dealing with electronic systems, electronic degrees of freedom, to the infinite range of the Coulomb interaction, because you can have a long range character of it, which will be linked to one particle, one hole excitations. A two particle, two hole excitation can often be linked to the short range aspect of a force. So you can actually interpret specific physical processes in terms of the types of interactions which you have. And the Lipkin model, the way we phrased it, is a model which bakes in some of these correlations which we think are important in physical systems. Okay, so let's write down these rules here. So we said that we should draw all distinct diagrams, topologically distinct, to give an order by linking up particle and hole lines with different interaction vertices under the restriction that the ordering of the interactions remains unchanged. So if one interaction comes at this stage, then the other one comes at the other stage. So we cannot flip them. This becomes in particular relevant when you do time-dependent perturbation theory. Or if you move into quantum field theory, you have processes at different times. And they represent specific physical decay processes or specific processes which then occur at a given time in the sequence of interactions. So the first condition is that the ordering of the interactions remain unchanged. That the ordering of the interactions So the ordering of the interaction vertices remains unchanged. We do not change that. Then the next one is that particle states remain particle states and whole state remain whole states. So that's the next stage. So we cannot change a particle state between the two interactions into a whole state. So particle states, so B, particle states remains as such, and whole states remain as such. Particle and whole states. And then finally, the ordering of the interaction at the beginning and end remains unchanged. So the ordering of the interaction vertices, or just the interaction of the interactions, at the end and the beginning remain the same. The end and beginning is unchanged. Then, next rule is that for each topologically distinct diagram, we then need to set up the interaction vertices. And for each of the interaction vertices, we have to either figure out whether this is a one-body, two-body, or three-body interaction. And from that, we have to set up the different labels, which then indicate whether there's a state to the left of the interaction and to the right. So the next step is for each topologically distinct diagram, for each distinct diagram, we would then, A, set up all the interaction vertices. So that these interaction vertices could be either of the two-body type or one-body type. We just write the one-body type with a cross here to indicate that this could be either Hartree-Fock term, it could be a specific operator which we're looking at of the one-body type, etc. There could be three-body types of interactions if we want to add that. But in this course, as we mentioned in the beginning, we're going to stay essentially with two-body and one-body operators. So we set up the interaction vertices which are relevant. And then for each one of them, we have to set up specific contributions. So we're setting up the interaction vertices. And when we have done that, because we have now performed the contractions, then each of these vertices, each of these vertices are assigned labels. And then I'm just going to set up the way you would assign the labels. So if I now have an interaction vertex of this type, so this is a V, a potential, and then I'm putting in a state definition, so P, Q, R, S, then that means that I have to extract an integral which looks like this. So P is the one which leaves at the left, Q the one which leaves at the right, and then I have the same for the incoming states. So this is a two-body interaction. Or if we have a specific operator, a one-body operator, so we often set it like this, and we label this as an operator, O, and we have a state P and Q here, that becomes simply P, and then we have the operator, which we just leave unspecified here, and Q. So these are two integrals which we typically will tabulate or will have to calculate on the fly when we are setting up the contributions on different orders in interaction. So that is this step, when we now have set up the specific topologically distinct diagram. Then we need a phase factor. So there is a phase factor, and that's the one which we had discussed before the break. And this phase factor is given now by -1 to the power of the number of hole lines plus the number of closed loops. So this is the number of hole lines. And each hole line actually represents a set of contractions where we have to interchange the operator so that we bring them close to each other. And we saw that when we calculated the contractions with specific hole states. And that gives immediately a rise to a change of sign, which is a sign -1 here. And then the number of loops, which we're coming back to. So this is the number of closed loops. So I'm coming back to the derivation of these specific factors, but keep in mind that everything which we have here simply comes from the usage of Wick's theorem and the anti-commutation rules for the operator. When we have that, we have a new factor which we need to plug in, and that is the energy denominator. So everything we are doing here now is actually to go back to this figure which we put up before the break, when we looked at the contributions in terms of an initial state. We have some interactions. We perform the contractions. Then there is an energy denominator here, which we have to account for. So that comes in between the states. So that's the intermediate difference between the energy of the intermediate state and the energy of the ground state. And what happens is that since we are defining these non-interacting states as the sum of single particle energies, then these differences here turn out to be very simple. So when we do many-body perturbation theory, the typical basis is normally defined in terms of the non-interacting basis. That's a very important thing to just keep in mind. And that means that these two guys here, when we subtract the intermediate state energy of a many-body state, this just ends up as a difference between all the single particle energies in the ground state and all the single particle energies in the excited state, which then translates into a difference between whole states and particle states. So what we get then is a new point here, a point D, and that is for each interval between successive interactions. For each interval between successive interactions, we have a factor, we have an energy denominator, which is given by the sum over the single hole states and their energies, epsilon I less than F, minus the sum over the intermediate particle states. And then we have an A larger than F of epsilon A. Then there is a final factor, which sometimes is a little bit more trickier to prove, but we saw already how that came through here. And that is a factor which is in this diagram here, which is a factor over 1/4. And this is related to the way we can twist the lines, because in this case, we have two particles leaving and two holes coming in, or two holes leaving and two particles coming in. And that puts a restriction on the number of types of contractions we can make. So that means that there is going to be a factor which is called the factor of equivalent pairs. So there is a factor which we are going to call 1/2 to the power of number of equivalent pairs. So NEP is the number of equivalent pairs. Equivalent pairs of lines, and they have to be the same, which start and end at the same vertex. Of lines which start, so this means whole lines or particle lines which start and end at the same interaction vertex. Finally, the last one is that we sum freely over all the intermediate particle states. Sum freely over all intermediate states. Okay, then there is even one, all lines should have a label. This is pretty obvious, should have a label, whether they are particle states or whole states. So let's look at the diagram now and see how we can extract the analytical expression for that specific diagram. And this is a typical diagram we're going to look at now to third order interaction. So suppose now I give you a diagram which looks like this. So I have a particle state, I have a whole state here, and then it looks like this. And let's put labels, because when you set up a diagram, you have to put labels on it. And this would be a state B, a state J, a state C, and a state K. So let's try to set up the mathematical expressions for it, using the diagram rules now. Now, one thing you can, if you look at this, what happens, the way you can think of it is that here you create a two-particle, two-hole excitation. This is the excitation of the ground state. Now, what happens here is that one of these one particle, one hole states can change into another one. This one particle, one hole state stays unchanged. And then at the end, we de-excite the two particle, two hole excitation, and then we are back to the ground state. So you would then have a change in one particle, one hole excitation. So in a certain sense, you can think of this as a one particle, one hole excitation. This is unchanged. Here you create a two particle, two hole excitation. You get a new two particle, two hole excitation here. And then this gets de-excited here. If we now want to use the diagram rules, we see now that the number of holes, n holes, is equal to 3. We have closed loops, n loops equal to 3. We don't have any pairs of particles which start at the same interaction and end at the same interaction, because this guy starts here and ends here. But the other particle pair starts here and ends here. So they have to end at the same interaction vertex. So in this case, the number of equivalent pairs is actually equal to 0. So there are no equivalent pairs. So that means that there will be, if you now have 4 interaction vertices, there will be 36 contributions here, which at the end sum up and cancel the factor of 1 divided by 4 to the power of 3. Then, if I now look at the energy denominator, so if you take that one, just to bring up the different pieces, what we get then is the following. So if I start at the bottom, let's do that. I would now have an energy denominator which is defined by the difference in the hole states I and K and particle states A and C. So the first guy is then, so let's just mark that one. So the first denominator, this one, goes in here, and we write it like epsilon I plus epsilon K minus epsilon A minus epsilon C. Then we take the next one, which is this intermediate state, and then we would have a contribution which gives us then, if we take this one and put it in here, then we would have an epsilon I plus an epsilon J minus an epsilon A minus an epsilon B. That is the energy denominator here. Then we have the energy denominators, number of loops, equivalent pairs, number of hole states. And the next thing we do now is simply to sum over all the intermediate states. So if we want the expression here now, what we need is the following. So we have a sum over A, B, C, I, J, K. There is no factor 1 over 4 to the power of something. We have the top interaction, which then would be, if we now take the top interaction and take this one, then this one would give us a I, J, V, A, B. And now I'm skipping this anti-symmetrization sign. The next one, since I have many colors here, I can actually play around a little bit with colors, which is not very often I do. If we take the next interaction vertex, which is this one, so that would give us a sum over a B, and then I have a K, and then V, J, and C coming in. And the final one would be an A of C and V, I of K. And then this is divided with the denominator, which is then epsilon I plus epsilon K minus epsilon A minus epsilon C, multiplied with epsilon I plus epsilon J minus epsilon A minus epsilon B. And that will be that diagram to the contribution to third order from this one particle, one hole intermediate state between the two particle, two hole excitations and the excitation. Let's, since we now are getting a little bit more ambitious, let's now look at the fourth order diagram. And then also try to analyze what that actually means. So let's take a fourth order diagram. Actually, you will be exposed to this in the second midterm, because there will be specific fourth order diagrams which you will need to account for. You're going to get a list of all diagrams, and by looking at the type of interaction you have, you can then rule out specific contributions immediately. So let's look at, this is just one of the many ones. And now we're going to set up the interaction vertices, and then I'm going to put in two smaller ones here. And then I have a particle state here, which I'm going to label with a B and C. Then I'm going to get particle states here. And I'm going to have a particle state here, which is going to be a D here. And I label this with an A. Now, this is an interaction where I now have a hole state, which goes down here. And I label that with a K. And then I have a hole state here, which I label with an I. And similarly, I would have a hole state here and a hole state here. So you have either to annihilate a particle hole state at the vertex, or you have, so a vertex is just one of these guys. This is the total interaction. It has two vertices. And at the vertex, you can either have a particle coming in and out, or a particle hole state being created or annihilated, or a hole state coming in and a hole state leaving. But you cannot have two Hall states coming into the same diagram, to the same vertex. Then we're going to put labels on those. So I'm going to label this as a J and this as an L. Now, the reason why I'm bringing this up is that this is actually an interesting contribution. So let's now look at this stage which you have here. This is something which we can think of as a two-particle, two-hole excitation of the ground state. If I look at this one, the last one, what we have then is that we delete the two-particle, two-hole, and then we are back to the ground state. So we would typically call this for a two-particle, two-hole de-excitation. But then something funny takes place in the middle here. So, and I just wanted to ask you guys, how would you label that specific state which you have between these different vertices? If you count the number of Hall lines and particle lines, what would that be called? So just to give you a hint, I have two particles and two holes. I would obviously call that a two-particle, two-hole state. So the first one is actually U. If you think of this specific here, it's actually us taking a phi, ij, ab, and then we have some interaction, and then we have the ground state. This is essentially what we set up there. But then in the middle here, we have something strange happening. Yeah? Say it again. If you count, then you actually have four particles and four holes. Because you would have, if you look at that state now, you have a Hall state L, J, K, and I, and you have particles A, B, C, D. So this is a diagram which you would call a four-particle, four-hole excitation. So I wanted to say a little bit about this because this links with the second midterm. And these are kind of interpretations which you will need to do. So if you look at this guy here, we would call this for a four-particle, four-hole intermediate state. Now, when you diagonalize exactly, so let's try to break this down into what you are going to see next Friday. So next Friday, we are going to look at a Lipkin lookalike, but it is an inverted ladder. So the model which we are going to look at in the second midterm is a model which is a kind of, as I said, a Lipkin lookalike. So we have the Fermi level here, but now we are going to have four states. So instead of the four particles, which all could have the same quantum number, we are going to look at a state which has a system which has four particles, but each one of these, I will call this a P equal to 1. So this just represents some quantum numbers which we don't need to specify. Could be the spatial quantum numbers, and then we have spin. So we have either spin up and spin down. So this guy here could then be the ground state. And this is something which we are going to set up in the exercise. Now, we are going to give you a Hamiltonian, and we are going to look at a system where you cannot break any pairs. So we would call these two guys here as two guys which are paired. So the only thing which the Hamiltonian can do for us in the second midterm is to promote pairs around in the system here. So we're not going to break pairs. This model is called the pairing model, obviously. And it's the basic model for superconductivity and superfluidity in physical systems. And it is actually the model which was introduced by Bardeen, Cooper, and Schrieffer when they won the Nobel Prize for describing superconductivity. So we are going to look at that as a model Hamiltonian, and we are going to limit ourselves to no breaking of pairs. So we're going to look at four particles in four doubly degenerate levels, which means that we have 8 slots. So the whole system here would be 4 particles, which we can distribute in 8 slots, which means that if you then do the combinatorics, you will get 70 states. However, we are going to limit the system to no broken pairs. Actually, the broken pair thing is something you will see in many spectra because it requires energy to break a pair. And many of the first excited states in such a system are states where you break one pair. You will often see that, and that requires often more energy to break pairs. Some physical systems have very strong pairing correlations. So if you go to the strong force, which you have among protons and neutrons, that is a force which has really strong pairing correlations. And you will often see in the spectra of nuclei that in order to get an excited state, you often need to break a pair because the particles are strongly paired. So pairing correlations play an important role in many physical systems. But we are going to look at the simplified case which captures the basic physics. So if you look at this system and we say no broken pairs, then the combinatorics becomes much simpler because then we will have 2 pairs and we have 4 levels. So the combinatorics is the binomial factor of 4 and 2, which means that in total there are only 6 states. So the states you can make then will be states, and I'm just going to write them in a more schematic way here. So you could now have 2 here, and then promote these 2 guys up here. So we could call this phi 1, for instance. Then we have 4 more ways by which we can do this. So we could now take this one and just leave it here and promote this 2 guys in the bottom up here. We could call this for phi 2. And then there's going to be something in between. And the final guy, so these are all 2 particle, 2 hole states. There are 2 more. So I'm not going to give you everything in a midterm because I want you to figure out which are the other ones, but that's pretty obvious when you do just the combinatorics here. And then the final one is a state which is going to look like this. And this is going to be a 4 particle, 4 hole state. And we are going to label this as a phi of phi. So the Hamiltonian matrix you will set up with that force is going to be a 6 by 6 matrix. So there will be an FCI, full configuration theory element in the second midterm. So you can diagonalize exactly and find the ground state as a function of the strength of the interaction. And we will play around with weak coupling, weak interaction, strong interactions, and then you will obviously see that the results will differ a lot from a mean field calculation. So the second midterm will contain full configuration interaction theory, Hartree-Fock theory, but then we're also going to calculate diagrams in perturbation theory. So keep in mind that perturbation theory is an approximation to the full diagonalization. So when you diagonalize exactly, what happens then is that you sum all diagrams in perturbation theory to infinite order. So you have the exact coefficients. So you remember that when last week, we looked at what we got to second order. If we now go back to the terms in second order, what we would have then, if we look at these terms here, what we said last time is that this term here, together with that one, was the second order approximation to the wave function coefficients which we get from exact diagonalization. So order by order in perturbation theory, you get a correction to the wave function. If I take this third order term, which you saw here, this one, then this would be the term which you would set up, but then the correction would be this one. So this would be the correction to the wave function coefficients from third order perturbation theory, and it will be one of them. Now, when we now set up this expression, there will be a fourth order correction, and The thing with perturbation theory is that at every order, you bring in a type of correlations which corresponds to, let's say, 3-particle free hole, 4-particle four hole, etc. So the 4-particle four hole correction from many-body perturbation theory appears first at 4th order, but then it appears only at 4th order in the interaction. When I diagonalize in this basis here, I will get all the 4-particle four hole coefficients to infinite order in perturbation theory. So what you're going to do in this midterm is actually to evaluate some of these terms and see if that gives you something which is closer to the exact diagonalization. Here roughly the picture. So it's us actually looking at what perturbation theory gives compared with exact diagonalization. And the thing which you obviously will see is that the strength of the interaction which you have here plays an important role on whether perturbation theory is going to do a good job or a bad job. Okay, so that's roughly the kind of outline of the project. So it's us bringing in basically all elements which we have gone through till now in the semester. So if we now want to use the diagram rules, so let's do that. And that's the final thing we do today. And the recorded lecture, which we'll put online, is going to discuss the mathematical derivation of these phase factors and also discuss what's called the link diagram theorem, which is an important theorem, which is also derived in, I think it's chapter 6 or 7 of Shavit and Bartlett. But let's now just practice a little bit, because in the midterm, I'm going to give you all diagrams to 4th order, and there are quite many, but most of them are irrelevant because you are going to get an interaction which only acts on creation of 2-particle two-hole excitations due to the symmetries which we are going to preserve. So here, if we now do the counting, we have 4 hole lines, n holes equal to 4. In this specific case, we would have 1 closed loop here and 1 closed loop here. So that is n closed loops equal to 2. So that gives a factor of +1. I have 1 pair of particles which starts at the same interaction and end at the same interaction. I have these hole dudes which begin at the same. So I have 1 equivalent pair here. I have 1 equivalent pair here. I have 1 equivalent pair here. And I have 1 equivalent pair here. So that's going to give me an equivalent pairs equal to 4. And that means that I will have a factor of 1/2 to the power of 4, which then, if I do the calculation correctly, should be 1/16. Then the next thing is then to set up the energy denominators and to set up the final expression. So if I do that, I need now to make a summation over all the intermediate particle states and all the intermediate hole states. So let's do that as a final exercise today. And then tomorrow, as I said, we don't meet physically, but you will get a recorded lecture. I hope you don't get disappointed and will miss me here, but I will be back next week. So. Okay, so let's look at the final expression. So we are going to get 1/16. There's a +1. And then we need a summation here over the whole states, A, B, C, D, I, J, K, L. So these are all the states which we need to set up. Then we are going to set up the different elements. So if you keep an eye on the figure which you had, there's going to be a whole state I and J leaving. I'm skipping this anti-symmetrization sign. There is A and D coming in. Then I have a new interaction vertex, which is next from the top and down. And that is going to be a K and L, the 2 hole states. And I'm going to have a V and the particle states B and C. This is multiplied with B and C. And then I have V and the states which are coming in there, which are I and J. And then I'm going to have the final one, which are going to be A and D and V and K and L. And this is multiplied with an energy denominator, which is going to be given. And now I just take the difference between the different single particle states, which I have in between each vertex. So there's going to be an epsilon I plus an epsilon J minus an epsilon A minus an epsilon D multiplied with, and now comes an interesting factor because this is a 4-particle, 4-hole intermediate state. So let's look back a little bit, because now I need to take into account all the particle and hole states, because I have 4 particles and 4 holes, and that will give me an energy denominator, which is going to be epsilon I plus epsilon J plus epsilon K plus epsilon L minus epsilon A minus epsilon B minus epsilon C. As you can see, I actually still know the alphabet. And then there is a final interaction, now the energy denominator, which is an epsilon I, an epsilon K plus an epsilon L minus an epsilon A minus an epsilon D. That's the final expression for this contribution. So in the second midterm, you will get a list of the possible diagrams, and they are actually listed in chapter 6 of Shavit and Bartlett. And due to the type of Hamiltonian we have, there is only a given amount of them which give non-zero contributions. And those which give non-zero contributions are those which we are going to evaluate. The interaction in our case is going to just be a constant, which means that all these terms will just be replaced by a constant which we could call G. So we are not going to evaluate any integrals at all. So I'm going to leave you as a small exercise, 2 examples. You can try to see if you can calculate the expression for the diagrams. This is a typical 3rd order diagram, which now is going to have particle states here. Now, I'm not putting labels. You will have to put the labels on it and to find the expression. But it should be pretty clear that we have 4 particles and 2 holes. So this is normally called a 4-particle, 2-hole diagram. Or, in more compact terms, a particle-particle ladder diagram. Because you can now think of going to 4th order, and you can have a new particle state, set of particles. So you can actually have this is a series of diagrams which you can sum up as a geometric series. And these are so-called particle ladder diagrams, because you see this looks like the beginning of a ladder. And it shouldn't come to a surprise that you can have replace the particles with holes, and you could then have a 2-hole ladder. So the 2-particle ones brings you up, and the 2-hole ladder brings you down. So these are the type of contributions which you can sum in principle to infinite order. So that is one of the examples I want you to look at. I've only put arrows. You would have to put signs on it. And then there is another type of contribution, which is this one. And this is also a 3rd order diagram. This belongs also to a series of diagrams which can be summed to infinite order. Because what you see is that you have a chain of particle-hole excitations. 1 particle, 1 hole excitations. And there is a series of diagrams which are called the Tam-Dankov and random phase approximation diagrams. These are also diagrams which would pop up when you do Hartree-Fock theory. And typically, these diagrams here, which you see with the closed loops, they're called tadpole diagrams. Norwegian tadpole is a rumpetroll. Okay. So try to set up the expressions there. I won't say more jokes about tadpoles because that can easily end up in something, yeah, not so fun. And the recording is still on. Okay. I leave that to your imagination here. Okay, guys, I'm going to stop here.